Welcome, neat aspirants, to another captivating installment in our journey through the realms of physics and chemistry. In our previous sessions, we have marveled at the mysteries of fluid behavior, exploring the concepts like angle of contact and the dynamic forces within the drops and bubble. Today, we venture into a new frontier, the captivating world of capillary action and viscosity. But first, let's draw the inspiration from the nature's palette. A montage of plants, each immersed in different colored waters, their color reflecting the magical dance of liquids within their vascular system. Now, imagine a humble paper napkin effortlessly transferring water from one beaker to another in a mesmerizing jiff. It is a testament to the power of capillary action, a force so subtle yet profound in its influence. And finally, let us pour our attention into the dynamic scene where water and thick liquids flow, each demonstrating its unique viscosity. From the graceful ascent of water in the beaker to the contrasting flow rates of different liquid. These visuals serves as a gateway to understanding the foundational principles of fluid dynamics. So dear learners, prepare to be enthralled as we unravel the intricate interplay of cohesive and adhesive forces and delve into the sense of viscosity. Sit back, relax, let's embark on the captivating journey into the world of capillary action and viscosity. Let's dive in. In this scenario depicting the immersing the capillary tube in the water, no water ascent inside the tube. The cohesive force among the water molecules are robust, resulting in the formation of a concave meniscus. Here, the capillary action prevails due to the adhesive force between the liquid and solid surface of the capillary, surpassing the cohesive forces within the liquid. Consequently, the liquid rises within the capillary tube. When the water forms a concave meniscus, the pressure inside the capillary tube at the water surface level, point B, is lower than the pressure outside at the same level, point A. This pressure disparity arises from the combined effects of cohesive and adhesive forces, leading to meniscus formation. This pressure gradient drives the capillary action, causing water to ascend into the tube until the pressure inside and outside reaches equilibrium at the same level. This deviation from the expected uniform pressure at the same depth is offset by the absence of water ascent. Contrary to the previous scenario, here the water ascends inside the capillary tube due to the capillary action. The adhesive forces between the water and the glass molecules overpower the cohesive forces within the water, enabling it to climb the capillary walls, forming a concave meniscus. This upward movement of the water balances the pressure inside and outside the capillary at the same level. The height of water edge ascent is determined by the equilibrium between the gravitational force and the capillary action, expressed as H rho g equal to pressure outside minus pressure inside equal to 2T upon capital R, where T is surface tension and R denotes the radius of a capillary tube and meniscus. Or we can say height of a water column in a capillary is H equal to 2T upon rho gr. Capillary falls occur when a liquid's cohesive exceeds its adhesion, resulting in an obtuse angle of contact, allowing the liquid to descend within the capillary tube. When equal amount of water and castor oils are poured into identical funnels, it is observed that the water flows out rapidly while castor oil flows slowly. This discrepancy arises from the internal friction within the liquid known as viscous force, and the phenomena is termed as viscosity. Viscosity is defined as the property of a liquid representing its resistance to flow arising from the internal friction between adjacent fluid layers as they move relative to each other. This friction is a result of molecular interaction within the fluid, although it differs from classical friction. For the steady flow of fluid over a fixed horizontal surface, the viscous force acting tangentially to the layer is proportional to the area of the layer and the velocity gradient. Denoting F as the viscous force, it follows that F is proportional to area A. F is directly proportional to minus of delta V upon delta X, representing the velocity gradient. The negative sign accounts for the opposition direction of the viscous force, leading to equation as F equal to minus eta A into dV by dx, where eta represent the coefficient of viscosity. The coefficient of viscosity of a liquid can be defined as the viscous force per unit area of the layer where the viscosity gradient is unity. The dimensions and the unit of coefficient of viscosity are m into L raised to minus 1 into T raised to minus 1, indicating mass per length per time. In SI system, the unit is Pascal second, while in CGS it is poise P, where 1 poise equals to 0.1 Pascal second. Therefore, 1 Pascal second is equal to 10 poise. Now, let us solve some numericals. Problem 1. A U-tube with both the ends open to the atmosphere is partially filled with water. Oil, which is immiscible with water, is poured into one side until it stands at a distance of 10 mm above the water level on a given side. Meanwhile, the water rises by 65 mm from its original level. Asked to calculate the density of the oil is. Initial level of the water is at point C. Now when we added oil, then water level has increased by 65 mm. Therefore, height of a water column becomes 65 plus 65, that is 130 mm. It is given that oil level is 10 mm above the water level. Therefore, height of a oil column is 65 plus 65 plus 10 mm, that becomes 140 mm. At the point M and N, the pressure will be same as the system is in equilibrium. Therefore, height of a oil column is 140 mm and the height of water column is 130 mm. Since the fluids are in equilibrium, the pressure at point M due to the oil and the pressure at point N due to the water is same. Therefore, height of a oil column into density of a oil into G equal to height of a water column into density of water into G. Simplifying the equation, we get density of oil equal to height of a water into density of water divided by height of oil. On substituting the values and simplifying them, we get as 928 kgs per meter cube. Problem 2. A capillary tube of radius 0.1 mm is immersed vertically in a container of a mercury. If the mercury column in the capillary is depressed by 3 mm below the general level of the mercury in the container, calculate the surface tension of mercury. Density of a mercury is 13.6 into 10 raised to 3 kg per meter cube. Given that radius of a capillary R is equal to 0.1 mm, which is equal to 0.1 into 10 raised to minus 3 meters. Fall of a mercury in a capillary, that is H, is equal to 3 mm which is equal to 3 into 10 raised to minus 3 meters. Using the relation for the depression in a capillary tube, H is equal to 2T upon R rho G. On substituting the values and solving the equation, we get T as 0.198 newtons per meter. As we draw near to the end of our enlightening session, I encourage you to continue your exploration of this fascinating concept. For more practice questions and resources, visit www.ginit.com. Before we part away, I, Avinash from ginit.com, extend my gratitude for joining us today. Don't forget to share your thoughts, leave comments, and subscribe to our channel for more enriching content. Stay tuned for our upcoming conclusion, where we unravel the mechanical properties of fluids. Until then, immerse yourself in the boundless wonders of nature's law. Happy learning. 928 kgs per meter cube.